Hey chemists, how you going? Welcome to our equilibrium video series. This is video 2 looking at the equilibrium constant and ice tables. So hopefully you've watched video 1, which is just establishing what that concept of equilibrium is, and also looking at some equilibrium graphs. So let's get into this one. First of all, this is equilibrium constant, which is Kc. Sorry, that equilibrium's cut off up the top there. So the equilibrium constant. So this is a number which quantifies or measures the equilibrium position. We established in the previous video that the equilibrium position can favor the reactant side or favor the product side. It's a quantity that indicates the extent to which a reversible reaction occurs. So again, from video 1, equilibrium reactions are kind of the concept of how far a reaction goes to completion, as opposed to the rate of reaction, which is talking about how fast the reaction completes. K is a constant, and the little c means it's being measured using the concentrations of reactants and products in moles per litre. So Kc has that unit of moles per litre. The square brackets is representative of concentration, and we've used that previously looking at acids and bases, where we're looking at the pH calculation. And the value of K, which is a constant, varies depending on temperature. So this is an example of the formula where we work out the equilibrium constant. So it is a formula. It's one that you would do well in memorizing. And once you do kind of know how it works, it's pretty easy to plug in and play. So this is our reaction. So it's in the form of A plus B in terms of reactants goes to C plus D in terms of products. The little letters here are representative of the coefficients of those reactants and products. So Kc is the concentration of C, which is our first product, to the power of the coefficient, multiplied by the concentration of D in moles per litre to the power of the coefficient, divided by the concentration of A moles per litre to the power of that coefficient multiplied by concentration of B to the power of that coefficient. So Kc is always looking at a forwards reaction. So it's the value that indicates the extent to which the forwards reaction occurs. The value of Kc is affected by a change of temperature. It's not affected by a change in the concentration of reactants and products. It's not affected by a change in pressure. It's not affected by adding a catalyst. So that's just a table summarizing the factors that affect the equilibrium position and the Kc value, the extent to which that forwards reaction is favoured. So students can sometimes get mixed up by overlapping the concept of equilibrium and rate of reaction. All of these factors affect rate of reaction. So you need to ask yourself, with the question that you're trying to work out, whether they're looking for an answer for rate of reaction or equilibrium, because your response will be different. So a catalyst has no effect on the equilibrium position or Kc. It helps to reach the equilibrium faster, but it doesn't change how much that equilibrium position is favoured, so the extent to how far that reaction occurs. It increases the rate of the forwards and backwards reactions at the same rate. So you get there quicker, but the position doesn't change. So the equilibrium constant for this example reaction here, so we've got 2A plus B and the equilibrium arrows to 3C. So to plug in and play, we would have the concentration of C in moles per litre to the power of 3, because that's the value of the coefficient, divided by the concentration of A squared multiplied by the concentration of B. So looking at the Haber process here, this would be our plug-in in terms of the Kc expression. So what does this equilibrium constant number end up meaning? if you get an equilibrium, and this can be slightly different depending on where you read it, so I've tried to surmise it as best as I can, and I apologize, there's a little bit of cut off here, so I'm just going to move this down slightly. If a Kc is greater than 1, at equilibrium the concentration of products is greater than the concentration of reactants. Reaction goes almost to completion, and equilibrium favours the forwards reaction. So what I mean by favours the forwards reaction is once that equilibrium is established, there's a greater concentration of products as opposed to the greater concentration of reactants, because products is what that forwards reaction is turning into. So you might guess that the Kc of less than 1 will be the opposite. So at equilibrium, the concentration of products is smaller than the concentration of reactants. The reaction hardly proceeds at all. The equilibrium favours the reverse reaction. Kc greater than 1 favours forwards reaction. Kc less than 1 favours reverse reaction or backwards reaction. So Kc measures how far that reaction occurs, to the left or to the right. Has nothing to do with rate of reaction, how fast it occurs. At a given temperature, a reaction with a high Kc value still may be very slow, and we'll continue to explore this concept as we look at some equilibrium practice problems, mostly in video 3. An important note is the concentration of any pure liquid or solid is always ignored and replaced by the number 1 when constructing equilibrium constant expressions. So essentially, it's a non-factor when we're completing those. So let's look at a couple of examples. Here's the first example. What's the equilibrium constant, or the Kc, for the homogeneous reaction specified here? So we'll be looking at the concentration of C, which is CO2, multiplied by D, which is H2O, to the power of the coefficients, divided by the concentration of A, which is CH4, methane, and B, which is O2. Make sure you put the powers in, squared and squared. So that's essentially just coming up with the expression. We haven't gotten to the number part yet, we're just practicing the substitution. So example 2, we've got our second reaction. So if you're working along with me, see if you can pause the video and do this Kc expression now. So here's our response. Just a note, states of reactants are products that are in the same phase, which means that it would be homogeneous. So the fact that the water is liquid means that it's not included in that Kc expression. It's not required because it's not aqueous. This is a solvent, not needed. So looking at those states, and if you see that liquid, then you're not including it in the expression. So looking at weak acids with less than 100% ionization, so acetic acid, the Kc is low, which means it favours the formation of reactants, favours the reverse reaction. Weak acid, low Kc, equilibrium favours reverse reaction, and we've learnt this from the acids and bases topic previously. The majority of species in this would be in this form, and the minority would be in this form. So let's try one with actual numbers. 4 moles of A, 6 moles of B we introduced into an evacuated vessel. At equilibrium, 2 moles of C was present. Calculate the Kc if the volume of the container is 1 litre. In order to work through this, we're going to utilise a type of table, which I'm going to call an ice table. It can sometimes be called a rice table. So you would draw up a table like this. You would have a line in the middle to distinguish the reactants from the products. The ice stands for initial, change, and at equilibrium. You've got your A and B and C and D. I've put the question back in here. So put what you know into that table. And I'll need to move up a little bit to capture this. So up the top, and sometimes this is called a rice table because you would put the ratio up the top here, alpha ratio, of these elements. Now if I go back, you can see it's a 1 to 1 to 1 to 1 mole ratio. So that's why we're putting 1 to 1 to 1 to 1 up here. Then we're going to start putting what we know. So we know that we have 4 moles of A. We have 6 moles of B. We have 0 moles of C. And we have 0 moles of D. At equilibrium, 2 moles of C was present. So at equilibrium, for C, we'll be putting a 2 there. Now some of you might be saying, why are you doing number of moles when previously you said you should be working out concentration for Kc? You might notice that the volume is 1, and if concentration is number of moles divided by volume, if it's divided by 1, this is going to be the concentration anyway. So now what we do is fill in the gaps for this table. So we think, okay, if we started with 0 moles and we ended up with 2 moles, or moles per litre, what's the change? First of all, are we increasing or decreasing? The answer is increasing. We're going from 0 to 2. So that's why I've got a plus there. I've got a 1 because that's my ratio. And the difference between this is 2. If the ratio was another number, then we'd be able to multiply by that coefficient. So 2. The next part I'd start to fill in is the rest of these orange brackets. Because the ratio is 1 to 1 to 1 to 1, and this number's 2, all of the rest of the numbers are going to be 2 as well. 2, 2, 2. Because we're increasing and decreasing by the same ratio, just like the graphs that we looked at in video 1. Then I can fill in the rest of the gaps. 0 plus 1 times 2 is 2, is going to be 2. 6, it's this one first. 6 subtract 1 times 2 is 2, so 6 take 2 is 4, and then 4 take 2 is 2. So the concentration of A at equilibrium is 2 moles per litre. The concentration of B at equilibrium is 4 moles per litre. Concentration of C is 2 moles per litre, and the concentration of D is 2 moles per litre. So that's how we use an ice table. Then we can work out the Kc value, because now we have all of those concentrations. So plug and play, Kc, put that in your calculator, you end up with 0.5 moles per litre. If Kc is less than 1, is this favouring the forwards or the backwards reaction? See if you can remember that. It is favouring the backwards reaction. So that means at equilibrium, the concentration of reactants would be greater than the concentration of products. And that's the case. We've got 4 and 2 compared to 2 and 2. So what if the container wasn't 1 litre? What if it was 750 ml? We adjust this when you substitute the values into the Kc equation. So what we would do here is, instead of just having the numbers that we obtained from the previous chart, now realistically that should say moles, but that's okay. What we would do is we would do that concentration equals number of moles divided by volume, So you would be putting that in there. What's the answer going to end up being? It's going to end up being the same thing because the ratios are the same, but it would change that value for concentration. What if we graphed this information if it occurred 15 minutes after the start of the experiment? Just like in video 1, you draw your axes, you have concentration, and you would have time. Or in this case, we're just going to stick with number of moles. It doesn't matter as long as we've got our slope the same. So we'll put time down the bottom, and we're reaching equilibrium at 15 minutes. So that's when it's going to flatten out. So you put a dotted line there just to help you when you're drawing it. So here we're starting at 4, so that's going to be A, and we end at 2, and steep at the beginning, flattening out. So B, start with 6, end with 4, 6, 4, that's where you end. There we go. C is going to start at 0, end with 2, so 0 to 2, there's our C, and our D is exactly the same. So there's a graph of that change. So now we'll do a second price table calculation. So the difference here is now we've got some coefficients added to this reaction. So I'll skip over to our table. So we have 4 moles of A and 6 moles of B, and our ratio is 1 to 2 to 1 to 3, which we'll put up the top. So we've got 4 moles of A, 6 moles of B were introduced, and at equilibrium we have 3 moles of D. So we're implying that there's 0 moles of the product. Calculate the Kc. So the difference that the ratios make is that now those coefficients are going to exist. So if we're going from 0 to 3 and we've got a multiplier of 3, what's our actual change? It's going to be 1. And now we can put that number into each of the changes. That will be the same, but the coefficient is going to be different. Notice that I've got positive here for my products because we're making them. We start at 0 and it goes up. The reactants, it goes down. We started high, we end up lower. And then we can do that multiplication or addition. So 0, add 1 times 1 is 1, equals 1. 6, subtract 2 times 1 is 2, is going to be 4. 4, subtract 1 times 1 is 1, is going to be 3. So that's where we end up with. We've got that 1 litre container again. So we can say 3, 4, 1, and 3 for our product. Put it into our Kc expression. So make sure that you're able to do that. So concentration of C times D to the power of the ratios, so to the power of 3. Put that in your calculator, you end up with 0.56, which tells us that this Kc also favours the backwards reaction, which means there's going to be a greater concentration of reactants compared to products, which there is, 3 and 4 compared to 1 and 3. Last calculation for our rice table. Here's the problem. Try this one yourself. Don't look at my solution until you give this a go. Trust me, that's how you learn. So let's go back to this. What changes Kc? Temperature. What changes equilibrium position? Temperature, concentration, and pressure. All of these facts may be used to produce the best reaction conditions, to increase yield, speed up reaction rate. The chemists need to optimize their reactions in order to get the most product possible. It limits the necessity to do a reaction multiple times in the lab and limits the waste on an industrial scale. They need a simple way to predict the outcome of changing certain reaction properties. And this is going to introduce us to the concept of Le Chatelier's principle. So guys, thanks very much for watching video 2. This was on the concepts of the equilibrium constant Kc and the use of ice tables in order to complete some calculations. Video 3 is going to be on Le Chatelier's principle. I'll see you then.